So we've seen earlier the regression problem where we have effectively to model a conditional probability distribution at the output of our predictor. Now we're actually switching to a new task. It's a classification task where again we will solve this task using the Vapnik block diagram. Again, we will need to model our predictor with a conditional probability distribution, but in classification, our target variables are distinct and discrete random variables rather than continuous. So in this kind of setting, I'll motivate the classification task with a simple use case. Is actually going to be called the radar problem, and that's what we will start with next. In this setting, the use case, the application we will see is a well-known application. Back in the Second World War, the Battle of England was won primarily from the erection of these towers. This was actually called the radar towers, whose job was to transmit a signal towards the France, where from France the Nazi airplanes were coming in to bomb London, and every time that this waveform was impinging into some large object on the sky, like a plane, it was returning back into what we call the radar receiver. And there was kind of a human operator over there on each kind of tower with an access to a kind of a telephone device over there. And every time that there was a strong return of a strong signal that was received in the radar kind of a receiver antenna, he was calling London, and millions of people were, the sirens were sounding, and millions of people were actually running to the tube stations to save their lives. That was the application. And this application is evidently present in any modern car today that has exactly the same ability to have radars located in the, let's say, in the front of the car, to send exactly the same signals, and every time that you have a feature in your car that it's automatic, what is called automatic distance keeping to the vehicle in front of you, that is exactly the same thing. It was returning back that reflection from the car in front, and a controller is actually trying to keep the velocities between your car and the car in front of you constant, and therefore maintaining desired distance between the two cars. But anyway, I will motivate it with this sort of application, which is the World War II application, because also back then, a lot of the terminology that we will cover today, it was also first invented. And just to see exactly what is actually happening here, we have some kind of a time plot of a quantity that we'll be calling x, and it will be designating for us the so-called signal strength of or received signal strength or power. And very simplistically, we have some fluctuating received power when we have a strong return from a plane. And in nights where we don't, the attacks were usually during the night, when we have no return, we still have some fluctuating signal power, much smaller than that. Our receiver is going to have just one knob. That knob is going to be called the threshold. We'll symbolize it with W. It's a scalar value, that it is anything that exceeds it is going to, let's assume that this threshold value is set to this kind of level. Everything that exceeds it is going to be called predicted. That is, not predicted, is we're going to sound the alarm, and anything that it is not exceeding it, we are going to not alert anyone, and we will call that the no attack case. So our problem is a binary classification problem, what we call binary, because our now target variable, as compared to that regression, can only take two values. One, we will call this the so-called positive condition, the attack is going on, and 0, we will be calling this the so-called negative condition. And our job here, now that we are in the 2020s, we are going to solve this problem of determining the value of that kind of threshold using kind of machine learning approaches. So we have, what we will do is we will task a military person over here to sit and observe what is really happening every single day. So first night records the signal strength x1 and records also whether an attack has happened or not. x2 the same way, and so on. If they survive, we will keep them. If they not, we have to replace them with somebody else. So xm, ym, that's our, let's say, we have aggregated m examples of what is has happened at our receiver. And as before we progress into specifying what is really the problem statement, I just want to convey some kind of an intuitive fashion of what's happening. So this was the so-called attack signal strength, and this was the no attack signal strength. The sort of time series of all these kind of observations, night after night. And we have the problem to solve is to come up with an optimal value for the threshold. You can understand that the threshold is quite critical in determining whether how the system operates. If we set the threshold too high, this means that we will be missing quite a lot of attacks, and evidently people will die. If we set the threshold too low, this means that we will be waking up everyone unnecessarily. The first night they will believe us and return to their beds disappointed somehow or relieved. The second night they will still believe us, they will go down to the tube, but after the third night they will stop believing us, and when a real attack happens, people will also die. So the system will lose complete credibility. So the choice of this W is quite critical. So our predictor, the y hat that we have to predict, at this moment in time we will treat this as a 1 and 0. Later will become a number between 0 and 1. Is also going to return our predictor is going to also to return 1 or 0 for the positive and negative condition respectively. Okay, so that is the problem statement, how to set up this W optimally. And as you can understand, I can just before in the regression kind of problem, we had introduced the probabilistic nature of every predictor. So what we will do now is we will draw two probability distributions. And let me just draw this probability distribution. Let's say this. So this is a probability distribution of X. We have here on the X-axis our signal strength. And one of them is going to be called the probability of X. And when no attack is happening. And this is the probability of X when the attack is happening. And as you can see, these two probability distributions can be easily obtained as histograms by just going back to our data tape, the data set that we have created. and recorded, and select all the rows where the y target variable is 0, and obtain this histogram, and visit all the corresponding rows where the y is equal to 1 and plot this corresponding histogram. So in terms of plotting the histograms, this is definitely a very, I will call it easy exercise. And as you can probably notice from the shape of these histograms, we have not really made any assumption with respect to Gaussianity or nothing like that. They are definitely plotted as non-Gaussian type of probability distributions. And the moment I have, and also another sort of evident thing that's actually going on with this problem is that there is a very strong overlap between the two histograms when we have the signal strength between no attacks and attacks. As you can see also here from the time series plot, there's a quite significant overlap between the two. And that's, of course, due to properties of radio wave propagation. The waveform emitted from this kind of radar station can be impinged on the sea surface and go into some kind of transverse other kind of paths, the so-called multipath fading situation. Some of you may have observed fading while listening to analog radio stations such as AM and FM. Back in the old days, these were the only radio stations that we had access to. And also you may have sort of experienced exactly the same situation where you are going in and out of coverage holes using your cellular devices. The important thing about the sort of overlap is that let's assume that I have selected here a value for my threshold W. And the moment I have, if you like, a threshold W, I can start defining certain areas under those probability distributions that will be of great interest to me. So I want to shade the first probability tail, which is this one. I want also to shade this and area, and also to say with horizontal stripes this area. Okay, so these three areas I think will be quite important. Now the overlap means that since there is no absolutely clear separation between the two probability distributions, we are always going to make some form of mistake. We're always going to have mistakes, and in fact we can clearly distinguish four conditions, and we will tabulate them with what we call the confusion matrix. On the one axis of the confusion matrix, we'll be assigning this axis to the so-called ground truth, and the other to the prediction, the y hat. And when the y hat is positive and negative, and this positive and negative agrees to the with the ground truth, then we will be calling this correspondingly true positive and true negative. In fact, it's actually quite common to write first the second letter as a mnemonic rule. Write first the second letter and put a word, the letter T in front every time that you have agreement with ground truth. In the case where you predict there is an attack going on, but you are wrong, you are prepending it with the letter F, stands for false. So we have false positive here. And here we have also false negative. We are predicting negative, but we are wrong. And therefore we have the so-called false negative events. The overlap, as compared to the case which is quite unrealistic in practice, where we have some form of significant separation between the two histograms, like this, and therefore it's easy to select something of a threshold W that will separate the two conditions perfectly. The so-called linearly separable case is not present here. So we are going to, so let me just delete it to avoid any confusion, is not present here. So we're always going to have, in other words, these two type of events present in our problem. And before I describe what was actually happening every time we get this threshold W to not be set optimally, when the threshold W is set too high, then we are missing the events that are actually attacks that are actually going to, will happen. And therefore we are going to be increasing our false negative. So we are predicting that no attacks is happening while in fact they are. And if the W is set too low, we are going to be increasing the false positive rate, and in fact we will be alerting sort of the people to go down to the tube, but unfortunately no attack is actually going on. Now that we have recognized that we're always going to make a mistake, as manifested by this confusion matrix, we are interested to just qualify these mistakes and quantify those mistakes by just understanding the probability of making a mistake. This is definitely the probability of when we make where our prediction y hat is not equal to the ground truth y. And this happens in two instances. The first instance is when we have the probability, when we make the prediction that no attack is happening, when in fact there is an attack happening, plus the events when we are making the opposite claim. And I think it's worthwhile now trying to understand what is happening in this, what are those probabilities and how they're related to this histogram we have plotted. The moment we have specified a threshold location over here, W, we have split the region into two parts. The first region is called R0 and the second region is called R1. And now that we have these region names, I think the region names are also intuitively kind of understood, because this 0 index here corresponds to the case where we declare anything, as we said, below the threshold W there is no attack. We are predicting no attack, so that's what the 0 is here. And anything above the W we are predicting an attack is happening, and that's why the 1 is there. We can actually start putting these probabilities, quantifying these probabilities based on the area under those curves. And I hope you all remember that probability for continuous random variables such as signal strength over here is sort of manifested by such kind of areas. So what I'm going to do now is I'm going to declare that this probability, the first probability over here, is equal to the probability that I am making a prediction such as my x belongs to the region R0 when in fact the ground truth is 1. So I converted the y hat is equal to 0 to all the events which are to the left of W, so all the events where x belongs to this kind of region R0, and do the same, belongs to the region R1 when y is equal to 0. So all the events of x greater than W, in other words, all x's which are belonging to the region R1. So it is exactly equivalent to those convention that I had about what is y hat is equal to 1 and what y hat is equal to 0. So this one, the probability that x belongs to the region R0 when y is 1 corresponds to the left tail of this probability distribution. So this probability distribution, but only the left tail. So you can see here that the whole probability distribution here, the whole histogram, is P of x comma y is equal to 1, but here I'm interested only for the x is equal to R0. So it's the summation of this vertically striped and this bubbly kind of area over there. So I am going to write it as an integral. Probability of x comma y is equal to 1 dx. And I'm going to take this and actually do exactly the same for the R1. Probability of x comma y is equal to 0 dx. And now if I actually start relating what I actually wrote here with the counts that I have counted, I can count through a random realization of this experiment from my kind of looking at the predictor output and looking at the ground truth over here, I can understand that this corresponds to the false negative rate, and this corresponds to the false positive rate. And definitely this is the false negative because I am actually predicting that no attack is happening, and in fact I'm wrong. And the corresponding here case where I'm predicting that the attack is happening, and in fact I'm also wrong. So the false positive and the false negatives and the false positives are related to the entries of the confusion matrix here that are definitely present and countable using this kind of histograms. And as we discussed, our role here is to find the optimal W, and I just want you to understand how visually we can be persuaded that in fact there is an optimal W, and that optimal W will minimize the probability of making the mistakes. You cannot make it 0 because, as we discussed, we do not face in this situation a linearly separable data set, but at the very least we can minimize the summation of false positives and false negative events. And imagine that you are moving that W in the left side over here, so we're trying to move this line to the left, and look what's happening as you're moving into the left. Gradually you will come so maybe 2 snapshots are enough to see what is happening. So in the first value of this W to the left of the previous kind of W, what we are actually achieving is we are going to, whatever we are losing in terms of area out of this vertically striped area, we will be gaining in terms of the horizontally striped area. Having said that, we actually start seeing reduction of this bubbly area. And this area will start to be reduced and reduced and reduced up to the point where we reach what we'll be calling the W star, the optimal W. And this optimal W is the W that minimized this probability of mistake, simply because in that location the bubbly area got eliminated completely, and the summation of the false positives and false negatives that included it is the minimum possible. So actually we can write that sort of optimizing the W towards W star will be done using the well-known to us stochastic gradient descent algorithm that minimizes the probability of mistakes, probability of making a mistake. So the misclassification error, or also called misclassification error rate. So this will be done Now that we have some kind of a visual motivation of what we're trying to achieve here, we now need to understand how we can also motivate in the next discussion an objective function, and that it is going to be suitable for our problem here, which is the classification problem, in a similar way as we have done with the earlier loss function we have used. Initially was called mean square error, and then it was also called cross entropy. So we'll do that next. So to come up with this objective function, before we go and discuss that, let's review the so-called classification metrics. The classification metrics that there are a couple of classification metrics will be of interest to us. They will be entirely based, of course, on the previously described confusion matrix. And the first metric I want to address is called the true positive rate. The second metric is, the true positive rate comes with many names. And many of them have been sort of originating from various kind of domains: electrical engineering, computer science, and others. So in computer science, this also is called recall. In electrical engineering, this is also called probability of detection, and many other domains quoted as sensitivity. It's one and the same thing, and I just want to mention all of them just in case you come across one of the many. So this is the ratio between true positive and true positive plus false negative. So this is a ratio that is definitely going to be of concern to us and of interest to us every time we have to evaluate a classifier. And the second metric that I want to quote, and to have some discussion about those metrics a bit later, is a so-called precision. And this precision is another ratio of true positive divided by true positive plus false positive. And if you follow this video where we have plotted these histograms in a binary classifier with the so-called radar problem, and you probably understood the trade-off that exists between false positives and false negatives as we were moving. In fact, as we were moving the value of the threshold W, we were changing the areas under those two histograms. And of course, here we were trading off false positives for false negatives in our attempt to find this optimal kind of W. In a very similar way, we can actually claim that now that we have those metrics, the trade-off between false positives and false negatives is evident over here in the following trade-off. So let me write this down. So we can say that because as W changes, there is a trade-off between false positives and false negatives. We can actually claim that there is a trade-off between recall and precision. Because recall and precision everything is exactly the same in terms of numerator and portion of the denominator, but only the false positives and false negatives are present there. So this is actually an important trade-off that will be of great interest to us, as we will always finding ourselves making that kind of trade-off for classification architectures we will be designing soon. The other metric is not really a different metric, but it's a way to present performance metrics, classification metrics, is this what we call the so-called receiver operating characteristic, and we actually call it receiver operating characteristic from those days in the 40s when they were deploying this kind of radars. And I will describe it as the curve that we can plot by changing the threshold W. In the x-axis over here, it is the false positive rate. also known as false alarm from those days, the probability of false alarm, PFA. And the y-axis is called recall, evidently the same thing as a true positive rate. And definitely we have a probability of false positive rate that goes from 0 to 1, and a probability of recall, a true positive rate that goes again from 0 to 1, because they are probabilities. And therefore we'll find this curve constrained by those values. And as we change the threshold, we will be able to draw such curves. Some of these curves are going to be like this. Let me plot 3 cases. So case, let's say A, case B, and case C. And I think it's reasonable to understand now what is the best possible classifier we can ever design, which is of course not achievable right now. And it's not achievable in any case we have such cases of overlap between positive and negative classes. And that point over here is, this is the sort of ideal and unrealistic operating point. This curve, as we discussed, is called receiver operating characteristic, or ROC. And each and every curve is being plotted by having a classifier and tuning, if you like, its parameters, adjusting its parameters, the threshold more specifically. And same here. This is supposed to be a diagonal line, 45 degrees. And let's compare between 3 different classifiers. Which one do we believe that is actually the best one? And it's actually a very straightforward kind of answer. If we draw, let's say, a horizontal kind of line, the classifier A is offering exactly the same performance as the recall, but at a much reduced probability of false alarm or false positive rate as compared to classifier B. And of course, much better than classifier C. And therefore, either we draw a horizontal line, or actually we can draw a vertical line. We can make the same argument. A is offering a much better probability of true positive as compared to B and as compared to C for the same false positive rate. And therefore, we can actually write this kind of reference relationship in this specific case. So recall and false positive are involved in plotting this kind of curve to give us a, if you like, a graphical view of how the classifier is behaving in various kind of operating conditions. And when we tune this classifier and we're choosing the W, the specific W star that we have seen earlier, we effectively operate at a specific operating point. At that point, we will be sort of constantly operating, and we will, in many senses, we will need to make different trade-offs between positives and false positives and true positives in various applications. So let me write this down, that each point in the ROC corresponds to a unique setting of the threshold W. So that is, as a kind of a short summary of a couple of classification metrics that will be of interest to us, and the receiver operating curve. And we will also have another curve called recall versus precision. This curve will be introduced in another video and will be discussed then. In an early video, we saw how maximum likelihood was motivating every the underlying, if you like, objective function of every prediction problem, and so binary classification will not be an exception. And we started with a regression problem, and we saw how maximum likelihood and cross entropy are ultimately connected. Now we recognize the functional form of the so-called binary cross entropy loss function, which is specifically for our binary classification problem. And we will be motivating this by recognizing that in regression we had a p-model which actually was Gaussian. In binary classification, we're going to need to actually have a probabilistic model, a probability distribution, which is really appropriate for our discrete random variables that are y's. So our form of my p-model of, let's say, a y given x, comma w, this y over here is definitely discrete, and in fact binary. So I have seen already in the discussion of the entropy video coin tossing, and I know that at that point I have quoted the Bernoulli distribution as the appropriate probability distribution for our model. And the Bernoulli distribution, let me write it with whole words over here, is given as y hat to the power of y, 1 minus y hat to the power of 1 minus y. Now let's spend some time kind of understanding this. If my ground truth is 1, this p-model of y hat of y, given x, comma w is simply y hat because the y is 1, so this is 0, and therefore this term whole is 1, so the only thing that remains is y hat. And in fact, this is a very important conclusion in a sense that from now on, in binary classification, all I need to produce at the output is a single floating point number between 0 and 1. So it's a probability, so it's going to be 0 between 0 and 1 for sure. I'll be calling this probability when y is equal to 1, the probability of y is equal to 1 given x, comma w. In fact, I can write it as p-model. And this is actually going to be called the posterior probability. And we recognize the term posterior already. We recognized it when we had this probability review lecture. And in that kind of video, we have actually seen that posterior, it means after we get to observe the x's, our data. What can we say about our target variable y in this case? So the posterior probability distribution is going to be called y hat. So that is what our classifier is going to, from now on, going to be producing. And that this posterior being a probability means that we are have inherent the ability to provide an uncertainty about our prediction. We are going to, let's say, report a 0.82 as, let's say, the output of the positive class. And this means that we are going to be 82% certain that we have a positive event at the output of our classifier. And if we have already reported the output of a positive event, then when we are dealing with the negative case, our p-model over here that we have selected of y given x, comma w will be simply be 1 minus y hat, because with y is equal to 0, then this becomes 1, and this becomes 1 minus y hat. So immediately we can actually get the corresponding p-model for the case of the negative case. In fact, I don't need to write anything else in this point. maybe I can do. Maybe I can write P model of y is equal to 0 given x comma w, and this was shown to be 1 minus y hat. So I don't even need to produce a vector in the output of my binary classifier. Just with one value, from that value I can deterministically obtain the other for the negative class. So if I have produced 0.8 for the positive class, then the probability of the negative class is 0.2. Okay, so that's kind of an important conclusion of this kind of discussion, and the Bernoulli distribution, which is obviously very appropriate for binary events at the 0 or 1, or the so-called coin tossing distribution of heads versus tails. And if I remember the maximum likelihood kind of discussion and the so-called cross entropy, in that kind of cross entropy, I had the following formula, which is equally applicable to any predictor. I had a y hat comma y is minus the expectation of x comma y, my examples, according to the so-called p data hat distribution, log p model of y given x comma w. And this is definitely the result that we have seen earlier, and just want to contrast that against what we have seen earlier. We had an underlying probability distribution where our data is, and definitely this p data hat distribution is effectively the table that we have seen earlier, the distribution that governs the training data or the data that we have recorded with all our kind of ground truths. So the p data hat distribution is present in here. So no changes from what we have seen earlier. It's just a different type of data. And I'm actually interested to go ahead and calculate this term over here. And this term can be trivially calculated as log of my p model is y hat to the power of y times 1 minus y hat to the 1 minus y, or log y hat to the power of y plus log of 1 minus y hat to the power of 1 minus y. And this is of course making the use of the log of the products is the summation of the logs identity, and this uses another identity. This is y log of y hat plus 1 minus y log of 1 minus y hat. And for those who remember the discussion of the entropy, we have seen a sort of identical kind of term in the presentation of the binary kind of entropy graph, the coin tossing, during the coin tossing experiment. So let's plug this into this formula, and at the same time we will replace the expectation with the sample mean. So from these two we can conclude that the cross entropy, the binary cross entropy, so I'm just going to put a capital B in front to distinguish for the cross entropy for multi-class problems. It is y hat comma y minus 1 over m summation from I is equal to 1 to m of yi log of yi hat plus 1 minus y I log of 1 minus yi hat. Definitely this is a very easy to evaluate. This is definitely a scalar, which indicates to me how well am I doing. And this is the loss function that is going to govern from now on our binary classification problem. And we need to use it as an objective function. And when we minimize it, equivalently, we will be reducing the probabilistic distance between the p data hat that is present in my data set that is actually given to me, And the P model, which, as we discussed here, is of the Bernoulli distribution. And now we can just go ahead and plot that. In fact, let me just go and plot this term. And this term can be plotted over here. So the x-axis, I'm going to plot it against the y-hat. The y-hat is for the probability of the positive. And this is my binary cross entropy. In fact, I will call this term the so-called inner term to avoid confusion with something that involves an averaging over many of those inner terms. For each of the examples and each of my predictions, I have obviously a term over here, a real number I can trivially calculate. So let me call it the inner term over here in the y-axis. And if I plot this term, then I will get something that is going to look like this. So the probability, let's interpret this graph. When the y-hat is 1, means that I am 100% certain that this is a positive event that has happened. And this means that the probability, so this curve corresponds with, I forgot to mention that this curve is plotted when y is equal to 1 for the specific ground truth. When my ground truth agrees with me, then I'm expected to get the inner term to be 0, as intuitively understood. I'm 100% in agreement with the ground truth here. On the other hand, when I'm predicting the y-hat to be 0.05 over here, and this means that I'm predicting the positive to be 0.05, and in other words, I'm predicting the negative to be 0.95. I'm predicting that no attack has happened with 95% confidence. Then I'm actually going to, and my ground truth disagrees with me, I am going to incur a huge loss. So I can actually sufficient to say here that BCE penalizes confident wrong decisions. Such as 0.95, but wrong decisions. And actually can draw also the kind of corresponding curve for y is equal to 0, and it should be symmetric. Obviously in the handwritten kind of way. They are not really symmetric here, but this is kind of quite important to realize the behavior of binary cross entropy, penalizing confident wrong decisions. So now we have everything that we need to draw a block diagram. And this block diagram is applicable, in fact, to all sorts of predictors. And we have already seen regression now in classification. So let me just draw the predictor as this box over here. We have seen then in the regression setting a linear model, a dot product, in other words, between the parameter vector and features. And we also seen here a classifier. We have not really discussed yet the functional form of what the classifier will actually be, but whatever this classifier is going to, so this is either for regression or classification. And input X is going to come in. In general, it has many dimensions. A y-hat is going to be produced at the output. And over here, we're going to have the, let's assume that this is now let's call it a loss function. And the loss function will be the mean square error or the cross entropy. In fact, we will show that the cross entropy is able to accommodate both mean square error as well, and as well also the binary quotient we have just seen. So the output of this kind of loss function, so this loss function should have some knowledge of the ground truths y, and we are going to obtain a scalar number of the loss and then this scalar number is going to be effectively fed into a block that it will calculate the values of the gradient of the loss with respect to the parameter vector w. And this is part of the stochastic gradient descent algorithm we have seen. And the output of this block is going to be called the parameter update. But it will accept a learning rate that we actually call eta. This will also accept as a hyperparameter the mini batch that we have actually called MB. And the parameter update formula will provide for us and will update for us the vector W of all the parameters involved inside this predictor. So this is a very generic block diagram that will allow us to train and therefore optimize any machine, any prediction machine we have seen up to this point.